Okay. Hello, everybody. Welcome to today's seminar. So we have our relatively new arrival, Myriam Mahaman, who come to us from Dresden, will be here in Prague for 2 years. So we're very welcome. And giving her first talk, and she will speak about the ring of differential operators on a monomial curve is a Hopf algebroid.
Thank you. So I would like to thank Julius because defining what a Hopf algebroid is quite tough. Okay, and thanks to that, I will skip a lot of details throughout the talk. Okay, so our goal, so this is joint work with Ulrich Kremer, my supervisor, and our goal with this project was to produce new examples of Hopf algebroids. So we start with a commutative algebra A, and we associate to it its ring of differential operators. Then it is known that when the algebra is smooth, its ring of differential operators is a Hopf algebroid. So the question is, can we find algebras which are not smooth, yet whose ring of differential operators is still a Hopf algebroid? Okay. So I will start by defining what is meant by the ring of differential operators. And as a motivation, we will look at Rn. So we think of it as a geometric space. And we are interested in the algebra of smooth functions. Okay. Then a differential operator on Rn is an R-linear map from the algebra to itself, which can be expressed through partial derivatives. So this is usually what we have in mind when we think of a differential operator. The question is then, if you replace the algebra C infinity of Rn with any arbitrary commutative algebra, can we find a way to define algebraically those operators? And so we will use a definition which was formulated by Grothendieck. So we work over a commutative ring, a commutative unital ring, and A is a commutative unital K algebra over K. Then the ring of differential operators on A is a subalgebra of the A-linear endomorphisms on A. It is filtered, and the filtration is defined as follows. So in order 0, we have the multiplication by elements on A, which is identified with A. And then for the higher orders, for n, we define them recursively with this definition where the differential operator of order n is such that its commutator with the multiplication operators lies in the differential operators of order n minus 1. So it is a strange definition. And so at least for the operators of order 1, we get the derivations on A. So derivations are the maps which satisfy the Leibniz rule. And the derivations of order 1 are exactly those of order 0, A, plus the derivations. Yes?
Verifying on endomorphisms of A, you take the A bimodule structure, that is so left multiplication is just multiply from the left and right. Multiplication is left multiplication of the argument.
Yes. Yes, but yes, I do.
You have like at least choices, right? You could also have the one other way around with right multiplication.
Yes, but I choose the left one. Okay. So in and A, We have two, okay. So we have the natural embedding of A into an A, where an element A is mapped to the multiplication lambda A, where lambda A of X is just A times X. Then with this embedding, I have, okay, and I identify lambda A with A so that I write A times F to be the operator. So if F is in and A, then A times F is the operator where I multiply by A after I have applied F of X. And on the left, so is I multiply by A before I apply it. Sorry. And when I talk about differential operators, whenever I mean the left action, I'm talking about this one. And as I said, when we look at it as a left A module, the differential operators, the module of differential operators of order 1 can be written as this direct sum. And therefore, because both A and der A are contained in the ring, then the subalgebra generated by those elements is also contained in there, okay, which is what we wanted. However, in general, the ring of differential operators is strictly larger. So let us look at a few examples. Okay. So the most straightforward example is the polynomial ring in one parable. In this case, its ring of differential operators is just the file algebra, where here partial is identified with the derivation by t. And this is the ideal case where every differential operator is written in terms of so elements of A and derivations. So an unusual case is the truncated polynomials. So as a geometric object, it's like a fuzzy point. And in this case, every linear map is a differential operator. So this is already an example where a counterintuitive example of where what we think a differential operator should be does not work anymore. And
so here you fix the n, right? And so
yes.
if n is bigger, does the sphere here get more fuzzy or less fuzzy?
It becomes more fuzzy.
So that it's getting shorter.
There's a question in the chat from Paolo. Is there a particular reason to restrict Q?
No, it's just to get an intuition for our first examples. But for the rest of the talk, I will mostly work over a commutative ring.
Okay. All understand the answer to this question.
Paolo, did you understand that was an answer to your question? Paolo?
Yes, sorry, I barely hear you. I mean,
Can you hear me now?
I hear Myriam, but I barely hear you. Yeah. That's fine. Thanks a lot.
Okay, good.
And okay, and then our third example will be the cusp. So I will go into more details later, but for the cusp, we have some generators. So L-2 and L-3, they are of higher order and they cannot be written in terms of derivations and elements of A. Okay. So this is the typical example we want to look at. So I will now give some theorems about some known ways to find out how the ring of differential operators look like. So the nicest case is when A is the coordinate ring of some smooth variety. So in that case, the module of derivations is finitely generated projective. And here we have this result that, so if Q is contained in A, that is one reason I used Q for the previous examples. So if Q is contained in A and the derivations are finitely generated projective, then the ring of differential operators is, so the ring of differential operators is isomorphic to the universal enveloping universal enveloping algebra of the derivations. So I forgot to mention it, but the pair A forms a Lie-Reinhardt algebra. And as such, we can construct this universal enveloping algebra. And we have, so this is the best case we can hope for. Another way to determine the ring of differential operators is to use extensions. So we embed A into an extension K, and then we use the differential operators on K to determine those of A. So this theorem was shown by, oops. So this is a theorem by Sweetler and Masson, where, so we use localizations as extensions. So here I have some assumptions which are common in algebraic geometry. We can think of it as, so a typical example is that K is a field and A is the coordinate ring of some variety. Then if we use a localization of A, then we can recover the differential operators of A by looking at those on K which restrict to A. And in this situation, we have that the differential operators on the localization is obtained from dA by taking the tensor product. So this is a property we will use a lot later on. Now, let us go into Hopf algebroids. So I will go quickly through the definition. So we want to have an A ring that is a K algebra H together with a K algebra morphism from A to H. Then a left bialgebroid, we say that H is a left bialgebroid if there exists an A coalgebra structure on H considered as a left A module, so that the co-multiplication is compatible with the multiplication of H. So here the difficulty is that the image of eta is not included in the center of H in general. And that's what makes this definition, what makes formulating the compatibility with the multiplication so difficult. Next, we say that the bialgebroid H is a left Hopf algebroid if this Galois map is invertible. Okay. And note here, in the definition of the Galois map, we use the right action for the tensor product in the for the for the domain of delta. And on the right, we have the tensor product as left modules. Okay. And finally, I will briefly mention here the notion of an antipode. So a left Hopf algebroid, in the sense of Schaumburg, does not necessarily have an antipode. And so there are also several non-equivalent definitions of antipodes for Hopf algebroids. And for our paper, we used the one by Berman Slakani, where we required the antipode to be bijective. But okay. So the typical example of Hopf algebroids are Lie-Reinhardt algebras. Okay. So it is a left Hopf algebroid with the co-unit and the co-multiplication defined in such a way that the elements of the Lie algebra L are primitive inside the enveloping the universal enveloping algebra. Okay. And as I said before, there is not necessarily an antipode, but the Galois map is always invertible. And in particular, this Hopf algebroid is co-commutative, and it is co-nilpotent and generated by primitive elements.
Comment on this fact that there's no antipode in general? Because if I look at this delta minus one, I see you have the co-multiplication, and then it's like applying the antipode to the first or second tensor factor, right? And this gives you this minus one here. But you're saying, so in this case, there's no antipode in general.
Yes. So the way to get an antipode for Hopf algebras is that we take the inverse of the Galois map and we hit one of the legs with epsilon. The problem is that for Hopf algebroids, the problem is that the co-unit epsilon, it is left linear, but not right linear. And in our previous, and in the tensor product used to define delta, we use, however, the right A action, and that's why it fails. So conipotent means that so we can define the following, the reduced co-multiplication on the kernel of epsilon. So here I use the left action, and I just take the send h to delta of h minus 1 tensor h minus h tensor 1. And then I can define the iterations of delta r. That's not n plus 1. N plus 1 times. And being conilpotent means that for any h, there will be some n for which the delta bar of h will be equal to 0. And this is natural here, for example. So the kernel of delta 1, delta bar is just the primitive elements. And in our case here, all the elements are generated by products of primitive elements, and that's why the conilpotency holds. But in the example we will see later, we will obtain something conilpotent, but which displays some unusual properties. Maybe I will add some more information. So for this conilpotency, we can define the conilpotent filtration as the kernel of all those delta n's. And if we work over, so this can be defined for any coalgebra with a distinguished group-like element. And if we were working with coalgebras over a field, then this filtration is a coalgebra filtration. So. And in our example later, we will see that this is not true in general over commutative rings. Okay. No. So our main question is, we want to know for which algebras A is its ring of differential operators a Hopf algebroid. So in our case, the unit and co-unit are fixed. The unit is just the embedding of A into dA, and the co-unit is the evaluation at 1. The problem is to find the co-multiplication. So especially for those elements which cannot be written in terms of derivations. And okay. And this question was one of Svidler's main motivations to define the notion of a Hopf algebroid. So he was, I think he was the office neighbor of Reinhardt. And I'm sure he noticed that at first that the ring of differential operators are, so ring of differential operators are isomorphic to Lie universal enveloping algebras of Lie-Reinhardt algebras. And we do know that those have co-multiplications. So what happens in general? So he used duality techniques to formulate a condition, a sufficient condition for which we have a co-multiplication. And this condition is satisfied by smooth algebras and for non-smooth algebras, which are similar to the truncated polynomials. The problem, however, is that this condition is very hard to check for a given algebra, and there has been no, so as far as we knew when we wrote the article, so this question has not been considered ever since Svidler's article. So which made it quite hard for us to find a way for our problem. Okay. So now I will introduce the descent technique we use to construct a co-multiplication. So the strategy is that we embed dA into a Hopf algebroid. And this part is easy because we have those theorems which tells us when dk is a Hopf algebroid and when we can embed dA into dk. The hard part, and where we made our contribution, was to restrict the Hopf algebroid structure of dk onto dA. Okay. So we choose k, which is a localization of A, and which is smooth over small k. Then we have these properties we have seen before. So dA is identified with the operators which restrict to A. dk is isomorphic to the is obtained by tensoring with K the dA, and we know that dk is a left Hopf algebroid. Okay. So now we have this diagram where iota1 is the embedding and iota2 is the map from dA tensor dA to dk tensor dk, which is induced by iota1. Okay. And we would like to use the commultiplication upstairs to construct the commultiplication downstairs. There are some issues, however, that iota2 is not injective in general. And we also don't know whether the image of iota1 by delta k is contained in the image of iota2. However, once we have a positive answer to these two questions, then we can just, we have automatically a commultiplication downstairs. And the solution we found is a property called local projectivity. It dates back from the 70s and it is known under various names in the literature. And there are also a lot of variations in how it is defined. So we used a version of it from Percus's PhD thesis. So we say that dA is ROV locally projective. So it has an A module. So it's an A module property. If every element D can be written in this form as such a linear combination where the coefficients are obtained by evaluating D on some elements A1, AN of A. And this property is nice because it lies somewhere between being projective and being flat. So we have this lemma here that if I have an embedding of A modules and dA is ROV locally projective, then tensoring with dA preserves the injectivity. So this means that dA is flat. And not only that, we have a description of the image of the map. So those are the tensors such that whenever I apply the DIs on some element A, then I should land back in the smaller module X. And thanks to this, we can apply that property to our distance problem. Okay. So if dA is ROV locally projective, then all the induced map iota n from dA tensor n times to dk tensor n times are injective. And we also have that the image by delta after iota1 is contained in the tensor product, the image of the tensor product. Okay. So the idea here is that we use the embedding of A into K. When I tensor with dA, then I obtain an embedding of dA into K tensored with dA, which is just dk. And when I tensor once more with dA, and this is just iota2. And so the injectivity follows from the local projectivity. And So, and the statement about the co-multiplication follows from the description of the image. So, using the previous lemma, I have that the image of iota 2 are those differential operators such that when I evaluate them, lies in A or any A in O. Now I choose an element D in dA. And I want to know whether its co-multiplication D1 tensor D2 lies in here. But we have that D1 evaluated at 1 at A times D2 evaluated at B. This is just equal to D of A times B. So this follows from the properties of the co-unit for a Hopf algebroid. But we do know by definition that an element of dA maps all the elements of A into A. And therefore, the properties is satisfied by D1 tensor D2. And we have what we want.
Stand by D1A, D2B equals D of the product twice.
It's
Maybe just
no, I should have mentioned it in the definition of a Hopf algebroid, but it follows from, so for any Hopf algebroid, we have that for any H, the co-multiplication and the co-unit interact in such a way that epsilon of H, so H1 is epsilon of H2 B is equal to epsilon of H1 B. So that's one property satisfied by algebroids. Proving it right now would take too much time, but okay.
you're taking the product of one side and turning it into a co-product of the other.
Yes, so it has to do with the action of thinking of epsilon as a map from A into an A. Yes, and that's also what motivates us for the differential operators, because that's a natural way to describe them, to think of them.
Okay, so I see that epsilon satisfies this, but now you're saying all of the differential operators also satisfy this property. No,
Not
okay.
so. Well, they do in the ideal case for the derivations, because in that case, because the elements are primitive, then partial of AB is nothing but A times partial B plus partial A times B. And we want to know if, even if we have things which are not generated by derivations, can we still have this property? Okay. Then, okay, so we have the co-multiplication delta A. And in the paper, we proved it for general Hopf algebroids. So by Hopf algebroids, I mean that we can also have a decent diagram for the Galois map. And we can make the same arguments and obtain also an inverse for the Galois map on dA. Okay, and in the general case, we replace dk with a Hopf algebroid H and dA with a subalgebra of H, which I will describe in the next slide. Then by the same argument with local projectivity, then we obtain all the things we need. Okay. So given a Hopf algebra H, we define H of A as those elements whose action on K maps A to itself. We do this using the co-unit epsilon. Then we have shown that if H of A is R of A locally projective, and the canonical map from the tensor product with K to H is surjective, then the Hopf algebroid structure on H restricts to H of A. And furthermore, this restriction respects the co-commutativity and co-nilpotency. When applied to the ring of differential operators, we obtain the following theorem. So those assumptions are those we needed for to get the embedding dA into dk, and the statement about local projectivity is what follows from the main result. So now we are ready to look at our main example, the cusp. So from here onwards, I choose K to be a field of characteristic 0, A to be the coordinate ring of the cusp, so K of t squared, t cubed, and capital K to be the ring of Laurent polynomials. So capital K is a localization of A, and it is smooth. So its ring of differential operators is isomorphic to a localization of the Weil algebra. And so it is graded. So it has a canonical gradient, which is induced by the gradient on K, where the element T is of gradient 1 and partial is of gradient -1. However, to have a nice description of the graded parts, we will write the elements in this ring as in terms of elements in T and T partial, which is of degree 0. And once we do so, we get that all the graded parts are the form T to the D times the polynomials in D0. And because A is a graded subalgebra of capital K, dA becomes a graded subalgebra of dk, and we have the following gradient on dA. So now we can determine the elements of dA by looking at each of the graded parts, and this is about looking at properties of polynomials. For example, if I have an operator D, which is described as t to the d times some f of d0, then when I evaluate d on some t to the I, then it will look like this. It's just f of I times t to the I plus d. So to find the elements of dA, I have that I want the polynomials f such which get rid of the i's for which t to the I plus d does not lie in A. And thanks to that, I have the following description of dA. And the elements, so the powers I, which are problematic, are exactly those for which I plus D is negative or I plus D is equal to 1. What comes next? And with this, I have a combinatorial description of the ring of differential operators. And thanks to this combinatorial description, we were able to prove that dA is R of A locally projective. So with our description, it is about statements about polynomials. That given a D in dA, I can always find some suitable polynomials Gi such that I can write D as the linear combination D to the Ti times Di. And with local projectivity, we have the Hopf algebroid structure. Okay. And to formulate the structure maps, I will first give some generators of dA. So as a K-algebra, dA is generated by the elements of A, the derivation D0, and the some special differential operators L-2 and L-3. Okay. And so they are respectively of order 2 and 3. And let us look at how their commultiplication is in decay tensor decay. So for D0, it's a derivation, so no thinking there. For L-2, we have this tensor, partial, where partial is not in dA. And therefore, we wonder, can it really be written in terms of elements in dA? And similarly for L-3. And
Partial, right?
yes.
Okay.
And so we know from the local projectivity that it is possible. And I will now show how the commultiplication looks like. So the co-unit is just evaluation at 1, and it gives 0. And for example, for L-2, we had the partial tensor partial, and it now becomes this complicated tensor product. And similarly for L-3. So what is interesting is that, so partial tensor partial consists of operators of order 1 in decay. However, it is not possible to do so in dA tensor dA. So we had to introduce operators of order 3, so this one and this one, in order to be able to formulate the partial tensor partial. And for L-3 also, we had to introduce operators of order 4. So this one, the D0 minus 1 times L-3 and L-2 squared, before we were able to describe it. And for this Hopf algebroid, we also have an involutive antipode. So now let me mention what is interesting about this Hopf algebroid with respect to conilpotency. So as I've said before, it is conilpotent, even though it is not generated by primitive elements. And we also have that the primitive filtration is not a coalgebra filtration. And so if it were a coalgebra filtration, then I would have that so the commultiplication would land in the care of that bar I tensor care of delta bar J, where I plus J is equal to N. However, as I said before, we needed to include operators of higher order in the tensor before we were able to write it down, and that's why the code-important filtration is not a coalgebra filtration here. Okay. And I will mention another property of that Hopf algebroid. So both the cusp and both the coordinate rings of the cusp and the polynomial ring in one variable are contained in capital K. And we can define the dA dB bimodule contained in dk obtained by taking all the operators which map B into A. Then it was shown by Smith and Stafford and Muhaski independently in 1988 that this bimodule induces a Morita equivalence between the category of dB modules and the dA modules. But we do know that both dB and dA are Hopf algebroid here. So in terms of their categories of modules, being a Hopf algebroid means that there exists a canonical closed monoidal structure on this category. So here I am saying it not precisely, but so this means that the base ring A is the monoidal unit. The tensor product of dA modules is just the tensor product over A, and the internal home is just the A-linear home. Okay, and using a decent technique, again, we showed that dk of dA has a coalgebra structure which is compatible with the dA dB bimodule structure, and therefore the Morita equivalence above is monoidal. And before we finish, I will mention the family to which the cusp belongs. So those are the coordinate rings of monomial curves. So they are the form A equal K. So they are the subring of the Laurent polynomials, which are generated by powers of T, where the powers A1, AN are chosen to be co-prime with each other. Then our result holds for such rings, that for such A, dA is orally locally projective, and therefore a co-commutative conipotent Hopf algebroid. Furthermore, for any two of such algebras, the ring of differential operators are monoidally Morita equivalent. Okay. And now I recall here the main results I discussed today, and I thank you for your attention.
From the audience.
So I know a result by Modak and Merchant, who proved the Cartier-Miller-Moore theorem for Hopf algebroids. I understand you have a counterexample to this, or to a generation to this.
No, it is not really a counterexample. So in the Murdoch and Schun, they establish an equivalence between So we have the category of Lie-Reinhardt algebras. Lie-Reinhardt algebras over A. And that of Hopf algebroids. Whose source and targets are equal. So in one direction, I can take the universal enveloping algebra, and in the other direction, I can take the primitives. So Murdoch and Schun showed that when we look at Lie-Reinhardt algebras, which are projective on one. So here we look at this subcategory, and here we look at graded projective ones. Projective Hopf algebroids. So those are the Hopf algebroids, which are okay. So conilpotent, and such that the conilpotent filtration is such that when we take the associated graded, all the components are projective. And so Murdoch and Schun showed that this adjunction reduces to an equivalence on these subcategories. And for the cusp so the cusp does not belong to this in this framework, because so the primitive elements, so the derivations are not projective, because the cusp is not smooth.
Okay, thank you. But my question was more like you found an example of algebroid which is conilpotent, but is not the universal enveloping algebra. Could it be right?
Yes, but so they formulated their theorem in such a way that it's not. So it does not. So our example does not contradict the statement of their results.
Also, not my question. Also, I asked him is a counterexample to a possible generalization.
To a possible generalization. Okay, so we do know that.
So just as we found a Hopf algebroid which is conilpotent, but it's not a universal enveloping algebra.
Yes. So we have. Yes. So our Hopf algebroid lives here, but yes, it's not. So, but so we only have an adjunction. So this example shows that we only have an adjunction, and we cannot obtain an equivalence when we go to the bigger category.
This thing I don't understand. So you take a subalgebra A of K, and so you're saying now I identify the differential operators on A with the ones on K that restrict to A,
Yes.
right? That map A into A. But wouldn't you need to quotient this further by the differential operators that vanish on A?
No, it's because we are working with a localization, and therefore a differential operator which vanishes on A is 0 in the first place.
Okay, so this quotient is not needed. Okay.
Mm.
Okay. Yeah, so this is good. This clarifies. And so second question to your theorem that showed you get a monoidal equivalence. So at least in the examples that we saw, you had a co-commutative Hopf algebroid. So in particular, this is a triangular Hopf algebroid where you take the R matrix 1 tensor 1, which means your monoidal category is braided, in this case, just using the flip. So then one could try to see if this equivalence is even a braided monoidal one. Did you look at this, or?
Yes, because Yes. So because we use, we have in here, we use this embedding to obtain a coalgebra structure on pk of PA using the one on pk. But we do know that pk is co-commutative, and that's why this coalgebra is also co-commutative, and therefore the associated functor will be braided.
Okay, so it is true that it's braided, but it's a bit boring because it's just a flip in
Yes.
all the cases. Okay.
So do you know anything about the structure of cusps that do not satisfy this GCD condition that you had?
So I don't know. So these were the ones we considered because the argument worked for them. I mentioned this result by Smith and Stafford about Morita equivalences, and there is the general version of it by Pensby and Nevins, where there they work directly with schemes, and they formulated the condition for which there is a Morita equivalence when working over these schemes. And so for those ones, so they call it the cuspidal morphism. And so this is the most general case. It need not be a curve. However, we have yet to generalize our argument in that setting.
The obvious question to ask is, what about when you go to the non-commutative setting? Does it become impossible?
So in a non-commutative setting, so this is what I want to work on. So there are several non-equivalent definitions of the ring of differential operators in the non-commutative setting. And and for those definitions, none of them has yet to consider any Hopf algebroid structure. Yes. And my goal is to formulate a definition for which I have, in a natural way, a Hopf algebroid structure, at least for the free algebra.
Perhaps the jet bundles have got a structure of Hopf algebroid somewhere. I mean, paper advertisement. There, we did put a structure of algebra, and with Ale, we are studying the Hopf algebra case, which might lead to a structure of Hopf algebra, maybe on differential operators. So we'll see. Stay tuned.
Okay.
And a new question: if you were saying that differential operators are becoming general, that would be generated by the algebraic derivation. Suppose you just consider more general things with derivations, twisted derivation.
So twisted derivation. No, it is not a naive idea, but it would be very tough because even so the differential operators are the case where we only have one group-like element, which is the unit. So including the twisted derivations means that we need to look at something larger, which includes the group-likes, which are the algebra maps. And I do not know if the tools we have available are able to handle such a large structure.
Questions online.
Oh yes, maybe I want to mention so the work of Uli with Blessing Oni, where they look at actions of Hopf algebras by differential operators. So there, the algebras they consider have some group likes, and they found a way to describe one of the differential operators of the cusp in terms of those group likes. So that is one interesting fact which could be interesting to explore.
Maybe another direction towards generalization is that you also look at higher dimensional varieties.
Yes. So this would. So the next step would be to go for such cuspidal varieties, which can be written in terms of higher dimensional semigroups. So, and the most general version would be the one by Bensby and Nevins.
More questions? Online, in presence? No? Okay. Then in that case, we'll thank Myriam again. So next week, we have our very own Tristan Bice, who will hopefully be back in health. I think, yeah, it is Tristan next week. The title is Degenerate Types Simplified, Dependent Types Simplified. Hopefully it is. We're in Conirna. Yeah, it'll be in Conirna. We see you there.